Look at this. It looks like concrete and steel, doesn't it? But to an engineer, this isn't just a wall. It is a battery. A massive, rechargeable battery that holds back the power of nature itself. For thousands of years, humans have understood that moving water equals work. We used it to grind grain, cut wood, and pump water. But in the last century, we learned how to turn that flow into the electricity that powers your lights, your computer, and the electric car in your driveway. Today, we are going deep, literally. We are going to tear apart a hydroelectric power plant to see exactly how it works. We'll look at the physics of falling water, the incredible engineering of turbines that weigh as much as a Boeing 747, and the massive magnets that push electrons into the grid. By the end of this video, you won't just see a dam, you'll see a machine. Let's dive in. Before we touch a single piece of machinery, we have to understand the fuel. And unlike coal or nuclear, the fuel here is gravity. Hydroelectricity relies on two fundamental variables: head and flow. Head is the vertical distance the water falls. Imagine dropping a water balloon from 1 meter versus dropping it from a 10-story building. The one from the building hits harder. That is potential energy turning into kinetic energy. Flow is simply the volume of water moving per second. Even a small drop can create massive power if you have enough water moving at once. The magic happens when we convert that potential energy into kinetic energy. The dam isn't just a wall. It's a tool to artificially increase the head to maximize that energy potential. Let's follow a single drop of water through the system. It starts in the reservoir. This is our stored potential energy. At the bottom of the dam wall, there are gates called intakes. Notice the trash racks? These metal grills stop logs, debris, and sometimes fish from entering the system. Once the water passes these, there is no going back. It enters the penstock. The penstock is the artery of the dam. It's a massive steel or concrete pipe that funnels water from the reservoir down to the turbine. This is where engineering gets critical. As the water drops, it speeds up. The pressure inside these pipes is immense. Engineers have to carefully calculate the angle and diameter to minimize friction loss but maximize speed. But what happens if the turbine shuts down suddenly? That rushing water would slam into the machine like a car crash, a phenomenon called water hammer. That's why you often see a surge tank. It acts as a pressure relief valve, giving the water a place to go so it doesn't blow the pipes apart. Inside this casing sits the runner, the modern equivalent of the water wheel. There are three main types. Type A, the Francis turbine. This is the workhorse of the industry, used for medium head and medium flow. See these wicket gates? They open and close to control exactly how much water hits the turbine. Type B, the Kaplan turbine. For low heads, like a wide river dam, we use the Kaplan. It looks like a boat propeller. The blades are adjustable, allowing it to maintain efficiency even when water levels change. Type C, the Pelton wheel. For extreme heights, high head, low flow, we use the Pelton wheel. It's an impulse turbine. High-velocity jets of water shoot out of nozzles and hit these spoon-shaped buckets, spinning the wheel like a fidget spinner on steroids. The turbine shaft connects upward to the generator. This is where mechanical energy becomes electrical energy. It works on Michael Faraday's principle of electromagnetic induction. The rotor is the spinning part, a massive electromagnet. The stator is the stationary ring around it, filled with copper coils. As the turbine spins the rotor, its magnetic field sweeps past the copper coils in the stator. This pushing and pulling of electrons induces an alternating current in the wires. This isn't just raw electricity, though. It has to be synchronized. The turbine must spin at a very specific speed, usually 50 or 60 hertz, to match the national grid. If it spins too fast or too slow, it could damage the grid. The electricity leaves the generator at around 10,000 to 20,000 volts. But to travel long distances to your house, we need higher pressure. Step-up transformers boost this voltage to 400,000 volts or more. This allows the electricity to travel hundreds of miles with minimal loss, eventually reaching a substation near you, where it's stepped back down for use. Hydro is renewable, clean, and reliable. It can turn on in minutes, unlike coal or nuclear. This makes it the perfect partner for solar and wind. In fact, we use pumped storage as a giant battery. When solar panels produce too much energy at noon, we use that excess electricity to pump water back up into the reservoir. Then, when the sun sets, we let it flow down again. It is the world's largest energy storage system. However, it comes at a cost. Dams flood ecosystems and block fish migration. Modern engineering focuses on fish ladders and run-of-river systems that generate power without massive reservoirs to mitigate these impacts. A hydroelectric plant is a testament to human ingenuity. It's a cathedral of concrete where we force the chaotic flow of nature to march in step, electron by electron, to power our lives. Next time you turn on a light switch, remember, that energy might have started as a snowflake melting on a mountain peak, traveling miles to spin a giant wheel buried deep inside the earth. Thanks for watching. If you want to know how this electricity actually gets to your house, check out our video on the electrical grid.